In the previous lessons, we looked at the weighted vertex cover problem, and we gave a 0,1 LP for that problem. And then, because the 0,1 LP is slow to solve, we relaxed the 0,1 LP by replacing every constraint that the decision variable should either be 0 or 1 to a constraint where the decision variable is allowed to lie between 0 and 1. And then, well, we solved this relaxed LP, and by then rounding the vertices of value at least 1/2 to 1, we got a valid solution. And because we had a relaxed LP, which is a normal LP, this runs in polynomial time. In this lesson, we're going to look at the approximation ratio of this algorithm. So let's again briefly review the algorithm. So here you see the LP. What we want to minimize is, well, the function that takes the sum over all vertices in the cover of the weight of that vertex times its variable xv, and the constraints are for every edge uv, xv plus xu is at least 1, guaranteeing that we put at least one vertex into the cover, and, well, we had the relaxed constraint on the variables that u is between 0 and 1 for every vertex u. Okay? Then we have this relaxed LP, which is a normal LP, and that we can solve in polynomial time. And then we had our threshold rounding, where we took threshold 1/2 and decided to put every vertex into the cover whose decision variable xv has value at least 1/2. Okay, now let's try to have a look at the approximation ratio of this algorithm. Okay, so I hope you remember that in general, to prove an approximation ratio, what you need to do is, well, you look at the value of the solution that you compute, and then you show that not directly that it's at most rho times the optimal value, but you do that by going through a lower bound. Right? We prove that the value that we get is at most rho times the lower bound, and that then implies that the value is at most rho times opt. So the first thing we always have to do is come up with a good lower bound. So let's see if we can come up with a lower bound for this problem. And the nice thing about this technique of LP relaxation is that this lower bound doesn't really depend on whether our LP is modeling weighted vertex cover or something else. You can always use the same lower bound. And that's what I'm going to explain next. So what's this lower bound? Well, here we have, in this case, the relaxed LP for the weighted vertex cover problem. Okay, and in the relaxation, we had this constraint that each variable lies between 0 and 1. In the 0,1 LP, we had that the value of the variable is either 0 or 1. So what does it mean? It means that in the 0,1 LP, we have a more strict constraint, a stricter constraint. So that means that any solution, any valid solution for the 0,1 LP is also a valid solution for the relaxed LP. We simply have more possibilities to pick the values of our variables xv. And if you have more possibilities, then obviously the solution is not going to get worse. It could only get better, or maybe stay the same, but it will never be worse. So what can we conclude? That the value of the solution for the relaxed LP, which here I denoted by opt relaxed, is at most, it's at least as good as the value of the 0,1 LP. Okay, so let's try to write this again, but now for the complete problem. So we start with the optimal value for the weighted vertex cover problem, which I denote by opt VC. Okay, I also have the optimal value of the 0,1 LP, which is modeling this weighted vertex cover problem. And because our model, our LP, is an exact formulation of the weighted vertex cover problem, these two values must be the same. If I would solve the 0,1 LP, then that solution, since it's an exact model, is also an optimal solution for the vertex cover problem. So these two things are the same. And now if we look at our opt relaxed, right, which is the solution, the value of the solution for the relaxed version, which is, well, the sum of overall vertices of the weight of that vertex times this decision variable xv. Okay. This value, opt relaxed, as we just saw, is, well, it was at least as good as the opt for the 0, 1 LP. So I get that my opt for vertex cover is equal to opt for the 0, 1 formulation of vertex cover, which is at least opt for the relaxed version. So, conclusion, I can use opt of the relaxed version as a lower bound for opt for my weighted vertex cover problem. Okay, now we have a nice lower bound to base our proof on, namely the solution opt relaxed to the relaxed LP. So, now we can do the proof, and I claim that my algorithm using LP relaxation for weighted vertex cover is a two-approximation algorithm. Okay, so take an arbitrary input graph G, and let C be the solution, the cover that we compute. Okay, so what's the value of the solution that we compute? Well, C is the cover that we compute. So by definition, this is simply equal to the sum over all vertices that we decide to put into the cover of the weight of that vertex. Now remember that when do we put something into the cover? Well, if its value is above the threshold, which we pick to be 1/2. Okay, so for every vertex in the cover C, xv is at least 1/2, which means that 2 times xv is at least 1. So that means that I can bound the sum over all weights of the vertices in the cover by the sum over all weights of the vertices into the cover times 2 times xv. Okay, so now, well, we can simply put the 2 in front. And then the next step that we do is, instead of summing only over the vertices in the cover, we're going to sum over all the vertices. Okay? And because these xv values are at least 0, the extra components that I add, the extra weights times this xv that I add, that's all positive. So by, instead of summing over C, summing over V, again, I can use that as an upper bound. And now what you see in this formula, you see 2 times, well, the sum over all vertices of the weight of that vertex times xv. But that was exactly the solution, the value of the solution to the relaxed LP. So this is equal to 2 times opt relaxed, and as we saw, that was at most 2 times opt for our vertex cover problem. So we have proven the following theorem, that we can solve the weighted vertex cover problem using this LP relaxation technique, and what we get is an algorithm that runs in polynomial time and gives us a two-approximation. Okay, and here, well, you see the proof summarized. What do we need to prove? Well, it should run in polynomial time. That's true because we relaxed the problem and a normal LP can be solved in polynomial time. We should prove that it returns a valid, a feasible solution. Well, that's true because we picked a threshold of 1/2, and we showed that with that threshold we're guaranteed to get a valid cover. And then, as we just saw, the approximation ratio of this algorithm is 2. And it's important to remember that we did that by comparing to a lower bound, and this lower bound is the solution to the relaxed LP. So, let's summarize. Okay, so what do we do when you want to solve a problem using LP relaxation? Well, the first thing you do is you try to model that problem as a 0-1 LP, right? Try to see what you minimize, formulate that in terms of decision variables, and write constraints for where that your solution should satisfy. Okay? Then what you do is typically the constraints that you get, you should also put 0-1 constraints, right? Because you typically either select something or not. And in terms of decision variables, that would be the decision variable is 1 or the decision variable is 0. Well, because a 0-1 LP is slow to solve, you relax that constraint. You say, my decision variables are allowed to be between 0 and 1. Then, okay, you write an algorithm which generates this relaxed LP and solves the relaxed LP. And then you have to somehow decide how to round these variables. Right? So you get values between 0 and 1, and you have to pick a suitable threshold t that you can use to decide which variables to round to 1, and those would correspond to, well, let's say in general, objects that you put into the solution that you select, and which variables to round to 0. Okay? Then, once you've done that correctly, you will get a valid solution in polynomial time. Then the question is, what is the approximation ratio of your algorithm? Okay? And for that, well, the proof is always very similar. So you can almost copy-paste the proof that we saw. What you do is you use the solution for the relaxed LP as a lower bound, and then using that lower bound, and also in the proof the threshold will show up, then using that you can derive what the approximation ratio of your algorithm is. Okay, so this LP relaxation is an extremely powerful technique, and actually here we just scratch the surface. I use this simple threshold rounding. There are many more rounding schemes that for certain problems give better results, but these are the basics that already work nicely in many settings.